Okay, so from the question, you know that L naught coordinate is 0.30 and 0. So 0.30 is the XA naught and 0 is the XC naught. And although you don't know the solvent flow rate because you are asked to find the minimum solvent flow rate for question A, but you know that the coordinate for Vn plus 1 is 1 and 0 because this is the YC at n plus 1 pure solvent, and YA not YAN plus 1 is 0, or rather 0 1 if you prefer to put it that way. So we put 0 1. Okay, so we can plot the known points on the graph. So first is L naught, 0 0.3 and 0 is here. So this is your L naught, and this is your Vn plus 1 at this point. And then you know that Ln, the raffinate concentration, XAN is 0.06, and that Ln, the point Ln must lie on the equilibrium line. So you can plot 0.06 on the tie line. Should be this one. So this is Ln, and then to find the minimum solvent flow rate. So after we plot the L naught, Ln, and Vn plus 1, we can draw an approximate tie line crossing L naught to get a V1 min. So let's do that. So approximating a tie line that passes through L naught. Okay, so you should by right draw a straight line. I cannot draw a straight line on the computer because the ruler will mess up with my screen. So this is V1 at minimum solvent flow rate. Then from this V1, then you connect the lines Ln and V1, because if you have this countercurrent stages, this is Ln, this is V1, and this is Vn plus 1. Sorry, the arrow is a bit off here. Okay, so L naught and Vn plus 1 must lie on the straight line, and L naught and V1 must lie on a straight line too. So we connect those two lines together. What color should I use? Okay, so you connect these two lines, and you connect these two lines too, to get a mixing point M at Vn plus 1 minimum. Okay, M at minimum solvent flow rate. So you can read the coordinate for XA and XC. Okay, at minimum. So at M minimum, XA minimum, it's not the XA that is minimum, the XA at minimum solvent flow rate. Okay, it's not minimum XA. So XA at minimum solvent flow rate, if you do it properly, you should get around 0.12. Okay, because I cannot draw a straight line here, but when I do it on paper, I got XA at minimum solvent flow rate is 0.12, and XC at minimum solvent flow rate is 0.58. So from here, we can solve for V1 minimum by using material balance. So if I use component balance, component A, so I can get XA min equals to L naught XA naught plus Vn plus 1 minimum. This is the minimum solvent flow rate times Ya n plus 1 divided by L naught plus Vn plus 1 minimum. So as the solvent is pure, so there is no A in the solvent, so I can cancel out this term equals to 0 because YAN plus 1 is 0. Then I can continue. So XA min is 0.12 equal to 1000 times 0.3 divided by plus 0, just in case, 1000 plus Vn plus 1 min. So you can solve for Vn plus 1 min. So Vn plus 1 minimum in this case equal to 1500 kg per hour. So the next question, question B, is that when you already specified Vn plus 1 equals to 2500 kg per hour, and now you want to find what is the number of stages. Okay, so you have this is stage 1, stage 2, and so on until stage n. So you have here L naught with XA naught is 0.3 and L naught is 1000, XC naught is 0. Here Vn plus 1 is 2500, Ya n plus 1 is 0, Yc n plus 1 is 1. And here you have Ln where Xan is 0.06. Here you have V1, Ya1 and Yc1. So you want to find first the mixing point. So you want to find Xam equal to L naught Xa naught plus Vn plus 1 Yan plus 1 over L naught plus Vn plus 1. So that's 1000 times 0.3 plus 0 because there is no A in the solvent, divided by 1000 plus 2500. Then you get Xam equal to 0.0857, which is impossible to plot by hand. So you can approximate it with 0.09 if you were to plot by hand. And then you calculate Xcm equal to L naught Xc naught plus Vn plus 1 Ycn plus 1 divided by L naught plus Vn plus 1. Put the numbers in. Okay. So you shall get Xcm equal to about 0.714. Then you plot this point M on the graph. So let's do that now. So 0.09 and 0.71 shall be around here. Okay, this is M. So this is your L naught. This is your Vn plus 1. And your Xan is at where Xa equal to 0.06. So and it should lie on the line, so you get ln there. So once you got the point M, you can connect the dots such that you get V1. So okay, I try to do my best to connect the dots in a straight line. So ln connect with M, so that gives you V1. Okay, now we want to find the operating point. So we connect the points L0 and V1. Okay. Okay, extend it. And then we connect the points Ln and Vn plus 1. Oops. Where is it? Okay, I try again. Ln and Vn plus 1. So you shall get the operating point. So you should do better because we can draw a straight line on the paper. So that is your operating point. Then from V1, you try to approximate an approximate tie line based on the two tie lines beside it. So let's approximate a tie line. Okay. So that is an approximate tie line. So V1 would be in equilibrium with L1. So this one gives you the L1. Then after L1, then you connect the points L1 with the operating point, such that here you get V2. Then after V2, you also approximate another tie line crossing V2 based on the tie lines beside it. So okay, that gives you L2 because V2 will be in equilibrium with L2. Then after you got L2, you connect L2 with the operating point. Okay, you connect L2 with operating point to give you V3. And then with V3, you approximate again another tie line. Okay, approximate another tie line until you reach Ln. So in this case, I only have to do it 3 times to get into L3, which is actually Ln. So in total, I have 3 stages. Okay, approximately 3 stages. So if you see, there are 3 teeth. So 1 teeth here, 2 teeth here, and another teeth here. Okay, so those are the 3 stages.